Hello and welcome back. We're excited to present part two of our ongoing project, the RC Pi Car, or now it actually has a proper name, the AutoMed RC Car. In the first phase, we developed a working prototype designed to automate the delivery of vaccines and medications within hospital environments. In this phase, we focus on enhancing its capabilities, especially in certain areas of testing, troubleshooting, and overall system reliability. Our goal is to move the project closer to being ready for real-world clinical application. All right, so let's briefly recap. The RC Pi Car is a Raspberry Pi powered vehicle designed for safe, efficient vaccine transportation across hospital departments. It features autonomous navigation, remote control capabilities, environmental monitoring, and obstacle avoidance. The concept was built around reducing human handling of sensitive materials and creating a more automated, reliable solution for clinical logistics.
Hello, my name is Cody. I'll be going over a few slides in this PowerPoint. Um, First off, we have the summary of achievements. This is where we had the hardware fully assembled and integrated. We had basic navigation and remote control, which was tested and worked. And then the prototype met baseline delivery and monitoring goals. So all the way back in part one, we reached several milestones. We successfully assembled the FreeNova car kit with the Raspberry Pi 4. We used the Pi 4 over the Pi 5 mainly because some of the sensors weren't tuned or did not work with the Pi 5. So we had to make sure we used the correct Pi, and it was the Raspberry Pi 4B, so not A version but B version. We built basic uh, autonomous navigation using infrared sensors. This helped us a lot for navigating in the dark. So if it's moving, infrared is great in the dark because it doesn't need actual like visual sensation of like what's going on in front of it. The infrared is kind of like night vision goggles essentially for it. Allows it to still see as if it's daytime without any issues at all. Um, and enabled remote control through VNC. We also integrated temperature sensors to monitor vaccine conditions during transport. This is critical, especially in a medical facility, which is where we'd want to implement this. And we make sure vaccines stay cool or warm depending on their use or dosage. This way they don't go bad while being transported, or if they're sitting in the transporter for over an hour, we want to make sure that the temperatures stay moderately well. These core features also laid the groundwork for testing and enhancements, which we're about to discuss throughout here, or my other group members, Austin and Contrell, will be discussing as well. This next slide here, we have our current objectives. This is for Capstone 2 current semester. So we wanted to test navigation accuracy and obstacle response, troubleshoot connectivity and hardware issues, and enhance software for reliability and user experience. So during this semester, our focus really shifted towards optimization. We wanted to test the car in simulated hospital conditions, troubleshoot any reliability issues, and begin making improvements based on real usage feedback. This included refining our path planning algorithms, addressing hardware alignment concerns, and improving communication between the car and the remote interface. It was about taking our base model and making it smarter and more stable. Because back in Capstone 1 in the first half, we got the physical model created. We put all the sensors on it. We made sure it ran, could pretty much boot up with no issues through the Raspberry Pi 4. So this semester, we focused heavily on making sure that the coding was the best we could get it and that the sensors were working the way we wanted them to, and tailored them the best way possible to work in a um, drive to this location, drop off this product, come back when it's done.
We began testing what we considered to be a beta version of the RC Pi car. We evaluated how well it performs under different conditions and tight corners, mixed lighting, and minor connectivity interruptions. We measured delivery times, and watched how it handled obstacles, and we tested its ability to recover if its path was blocked or rerouted. These tests gave us a solid benchmark for the system's reliability and areas for improvement.
Troubleshooting was a constant throughout Part 2, or 499. One of our biggest issues was camera positioning. It wasn't giving us the visual field we needed for smooth navigation, so we repositioned it and recalibrated it. We also refined the motor control logic to prevent jittery or inconsistent movements. Another improvement came from optimizing our remote control interface by reducing lag in the VNC connection, which had previously made manual control a whole lot harder in real time.
After identifying the key issues, we made several enhancements. The biggest enhancement was improving the car's ability to recalculate if its route was interrupted. We also improved the alert system so that the low battery or signal loss triggers a notification to the user. On the interface side, we added more visual feedback to let users know when deliveries were complete and when the system was idle and when it required attention.
All right, and moving on to some updated user scenarios. Based on these updates, we revised our core user scenarios. In one case, staff can now reroute the RC car in real time using the interface if a hallway becomes blocked. We have another scenario where the car detects a low battery and sends an alert even if it's mid delivery, allowing a staff member to redirect it to a nearby charging station. And finally, we implemented a return to base feature. So after completing a vaccine or medication delivery, the car can autonomously return to its starting point for its next task.
Anticipated results and benefits is our next slide here, which involves faster delivery times, improved obstacle handling, greater reliability in clinical simulations, and higher staff confidence using the RC Pi car. With these changes, we're seeing major improvements in system performance, delivering times have dropped, and CART is avoiding obstacles more gracefully, and user interaction is smoother. These upgrades not only make the car more efficient, but also increase trust among the hospital staff who might eventually operate it, and it's become less of a prototype and more of a usable product. Trust is very important when using a product, especially if we're trying to deliver it to a larger company or even like a hospital that's managing very like critical patients or delivering um, medical product that needs to be there on time. You want to make sure your product isn't failing, it's not like running into a wall or obstacles in general, and that it's actually turning on and moving like it needs to. It's important that staff can trust that product because if they don't, they're never going to really use it, or they're going to not take the training as serious as they expect that it's going to be a useless product in the end and they're going to drop it and use something else.
So, what I will actually demonstrate for you now is essentially how our testing scenario went. It's a diagram version of it, so you can actually kind of get a clear view of what actually happened in the testing scenario. So what I'm going to do is I'm actually going to share my screen and show you essentially a layout of a hospital unit and what actually transpired, right? So this would be some example of actually of a typical hospital unit. Honestly, it's a little bit more than typical. It's a little bit fancier with this way that it's laid out, um, but it will do the trick. So essentially, what was happening was you have a patient room here where a nurse is located, right? The actual RC car is going to be located near the medicine prep room, aka wherever an Omnicell is. An Omnicell is basically the pharmacy on the floor. So if you need medications, you would actually go there. You would do all your boop 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 stuff for validation, security, and stuff like that. get your meds, come back to the room, and depending on whether or not it's a contact room, contact means that you actually had to actually dress up to go into the room because that person has some sort of illness that is transmitted by contact. The car would be located here, and the nurse would be in this room. Let's just call this room, for example, 5108 or something. This is basically going to be somewhat behind the nurse's station. The nurse here would actually send out a request for medicines, vaccines, whatever. So that would be put in the car, or in future iterations, the car would actually grab medicine by themselves. And the car would know exactly where the nurse is, location wise, by two infrared sensors. That is what we had. We had one sensor here that was basically saying, okay, this is the base. And then for the example of the scenario, we had one sample, or excuse me, one sensor here just to say, okay, this is where you're going. So they sent that off, right? The car received that request. We had put a tiny little like Tylenol pill there, personal pill there, just to simulate what it would look like inside of the little lockbox. And then what had happened was the car took off. Now, me personally, I was actually located over here because I was the obstacle factor. I threw a bunch of linen. I threw a bunch of towels right about here, somewhere in the path of the car that I knew the car was going to go. Car stopped for all of 2, 3 seconds and avoided said obstacle and made its way to the nurse that requested the meds right outside of the room of 5108. We did that scenario 3 times. One of the times, not even gonna lie to you, the car may have actually went a little bit past where it's supposed to be, but essentially 2 out of the 3 times it did stop where it was supposed to stop. And it did successfully avoid the obstacles, which you will see in the following slide.
Hello, and welcome to the testimonial section of this presentation, which wasn't meant to be a standalone video. Initially, we actually set out to test the prototype in a clinical setting around mid-February, and we were waiting for a video release from Duke University Health System. We actually got that release back, or at least we got a notification that our release was denied. As you can sort of kind of think about it, there's 3 people who don't necessarily have a name under their belt trying to test something in our hospital. They were not having it. So we actually had to do a supervised dump, which means that somebody that's in charge of the video release, and I want to say they were part of public relations, they had to supervise us while we actually deleted our footage. But the footage that they did say that we could keep was the testimonials from 3 nurses that we actually got to participate in this clinical trial. I hope that you enjoy, and here we go.
My name is Aisha Tilley, and I am a nurse here at Duke Regional Hospital.
Laura, and I work at Duke Regional as a registered nurse.
Deborah Brooks, nurse at Duke Regional Hospital.
Love that, love that, love that. Can you tell me about what you witnessed with the automated prototype?
Yes, so I placed my order online for medications,
So I pushed the button to order the medication.
and I saw it come down the hallway.
I could see it coming down the hall, and then the linen cart got in the way.
But then somehow linen fell out the closet. It stopped it in its tracks, but it was able to go around it.
So it kind of ran around it, you know how you think, so we just avoid it altogether.
And it brought it to my room that I was at, and I scanned my badge, and I was able to get my meds from the little device.
Very efficient.
It brought it down the hall to me. I did have to walk a little further to get it, but it still brought it up.
Can you see any usefulness?
I can, because unlike our tube station, we would have to stop what we're doing, leave the room, go to this tube station and get our medicines or get our lotions or creams. But with the new device, it can come directly to us, so we don't, if we're like in isolation wear, we would have to we don't have to get out of isolation, where it can just come straight to us and we have what we need.
I think that it could be used in a lot of different ways. For example, if we have a patient that's on contact, like COVID, and we need blankets or wipes brought into the room, we could get it to bring it to the room. That way we wouldn't have to gown out waste materials to have to go back in.
Oh, lots of uses. I can be used as a guide to help lost patients. I mean, it could take stuff from us to any part of the hospital. Usually people, my side, you know, a big heavy doing a whole lot of bending and stuff. So it would help me because it would be like a level. You know, it would tend to, as opposed to me having to bend down at the bottom of the omnicell and get something in the bottom drawer, or reach to the very top and get something at the top.
Can you think of any improvements?
The only improvement that I would see for the device is a security measure, only because it can be easily taken because it is so light and so small.
One improvement that I would say is, like I mentioned earlier, it did go a little further past the room that I was at, so it could be more precise on which room it stopped at.
Lovely. Thank you so much.
You're welcome.
Thank you. See? All right. Fantastic. Thank you.
You're welcome.
If we had the means to take this even further, we have a few exciting ideas. For example, with access to more advanced sensors like LIDAR, we could drastically improve the navigation and make pathfinding more dynamic. If we could partner with a hospital, we could offer live clinical testings, which would provide valuable feedback and refine our design. If we allowed the time, we'd love to build a full-scale management dashboard for hospital IT teams to control and track multiple units. And with funding, we would explore multi-floor navigation, including elevator integration, and far more expansive hospital layouts.